All right, good morning. So our goal today is to pick up where we left off and to finish the chapter 7 on energy conservation. Uh, the concept itself is fairly straightforward. What we found last time was that there are a certain class of forces that we call conservative forces. And the thing about conservative forces is that those forces always do work in a super predictable way. We find that conservative forces will always do zero work if you go over any round trip. In other words, a closed path, the total work by that force will always be zero. And if that's the case, then we can write what we call a potential energy expression for that force. And we learned one of those potential energy expressions, and that was for gravity, the gravitational potential energy was given by mgh, where h is the height of the object. M is the mass of the object, and g, of course, is 9.8. So anytime you see u, you're going to read that as potential energy. Now, what's meant by potential energy? It's the energy stored up by an object's position. So in this case, the higher the object is, the more energy it has stashed away. And if you were to lower it down from that height, you would get all of that energy back. It hasn't been vanished forever. Gravity has stashed it away, and it can give it back to you as you drop back down. And what we were using this potential energy expression for was if I had a situation where all of the forces acting on the object were conservative forces, you could find that the total mechanical energy, K plus U, where U is the potential energy and K is the kinetic energy. Just to remind you, kinetic energy is 1/2 mv squared. That total mechanical energy would equal the ending total mechanical energy. In other words, the energy you start with is the same as the energy you finish with. And so we were able to learn how to solve problems utilizing this sort of technique. Let's do some more. Let's try another example. And as you've probably noticed by now, I'm a gigantic comic book nerd. So let's do an example of the world's greatest superhero, who, as we all know, is Spider-Man. And Spider-Man is going to start off at the top of a building. And what he's going to do is he's going to spin a web, and he's going to swing on that web to a lower position so that sometime later Spidey is swung down to some lower position. And let's imagine that as he swings, he's going to sweep out an angle. And just from the way that I drew this, let's say that that's a 70-degree angle. And if his web line has a length of, let's say, 3 meters, what I would like to figure out is how fast is he going when he gets to the bottom. And just to make things interesting, let's have Spidey have a running start. Rather than have him start at rest, let's have him run off the edge of the building so that when he's up here, he's going to have a velocity of, let's say, 5 meters per second. So that's my goal. I know how fast he's traveling originally. I know that he's got a 3-meter long web line. He's going to swing down until he swings through a 70-degree angle, and I would like to figure out what his speed is at the bottom. Now, I can figure this problem out, but or by using energy conservation, but I am going to have to use some clever thinking to get around some information that the problem didn't tell me. So let's start with the easy part. We know that we're starting with the expression that the total mechanical energy that Spider-Man has to be conserved. Now, his initial kinetic energy, we know that kinetic energy is 1/2 mv squared. And when he started out, he had some velocity. So that was non-zero. So K initial is going to be 1/2 times whatever Spider-Man's mass is, which I don't know off the top of my head, times his initial velocity squared. Now, that's his kinetic energy. His potential energy I'm going to get from the gravitational potential energy, mgh. But here's where things get a little bit tricky. Because when it comes to measuring the height, I don't know how high he is. I did not specify how tall that building was. So what's going to happen is we're going to run into a little bit of an issue because we're not going to be able to figure out an actual number for his height. However, here's something that we have going for us. When it comes to this formula mgh, what we call height 0 ends up being arbitrary. You can always call any location you want height 0. And any height above that is going to be some positive height, and any height below that is going to be some negative height. So what I'm going to do here is, if this is his starting location, I can always choose, if I want to call this location height 0. And that's what I'm going to do. Or better yet, if I wanted to, I could call this location height 0. It doesn't especially matter. Sometimes the math will be a little bit easier for one versus the other. This is probably not the optimal choice, but it helps you to be able to solve non-optimal choices anyway. So let's go with that. Let's call this location here height 0. Now, if I do that, that means that his initial potential energy, mgh, is going to be m times g times 0. So effectively what I've done is I've made that equal 0. Now, when I get to K final, he will have swung down some distance, and he'll be picking up speed the entire way down. So what I know is that when he gets down here, he's going to have some final velocity. It will probably be faster than the 5 meters per second that he started with, but I'm not sure how much faster. So we're going to have to solve for that. When it comes to U final, we're going to go back and use mgh. Except now what's going to happen is I got to know what height this guy is at. And this is what's going to make things tricky. So I have this line here going straight down. I have this angle here being 70 degrees. So what's going to have to happen is, if I were to go, this is height 0, I'm just going to draw a little dotted line at height 0. Then obviously his height is going to be some distance that is below 0. Well, on my picture, I can visually see it. Let's change color so it'll stand out a little bit better. His height is going to be this distance right here. I need to find an expression for how long that is. Well, in order for me to do that, let's figure out other lengths. And the fact that I've got this nifty little right triangle here is kind of a clue. So if this is a 70-degree angle, this angle right here is a 20-degree angle, this angle right here is a 90-degree angle, and I know that this length here, the length of his web, is 3 meters. But if I know that this is 3 meters, I could figure out how far that is. Now, how will I do that? SOHCAHTOA, sines and cosines. And for this, this is the opposite side of the triangle. So I can either use the 70-degree angle and call that the cosine of 70, or I could use the 20-degree angle, use the sine of 20. Let's use the cosine. Why not? So up here, I know that the cosine of 70 degrees is going to equal the adjacent side. I'm just going to call this x over the hypotenuse, which is 3. So that means that x is going to equal 3 times the cosine of 70. And that's a number. So 3 times the cosine of 70. That tells me that that's 1.02 meters. But if this is 1.026 meters, and the whole web line is 3 meters, that means that this right here has to be a length of 3 minus 1.026 meters. So if I subtract off, that tells me that Spider-Man at this location has to be about 1.974 meters below where he started with. So this distance in red is 1.974 meters. So if I call this height 0 and I am this far below height 0, his new height has to be this, except since it's below 0, I have to slap a minus sign on it. He's at a negative height. Positive 1.974 meters would have been him swinging up higher than he originally started, and that's clearly not what he did. So when I go down here to do MGH, I'll add plus MGH final, but H final is going to be this number right there. And you'll notice that once I've done this, once I've written my energy conservation equation, the mass of Spider-Man, which I didn't specify, shows up in all 3 terms. And that means if I divide everything by m, it's going to cancel anyway. I don't even need to know what Spider-Man's mass is. If Spider-Man put on a few pounds, he's going to swing just as fast. If this is Miles Morales, he's going to go the same speed as Peter Parker. Doesn't matter what their masses are, the swing's going to be the same. So now, what am I solving for? I'm solving for his final velocity. So I need to get v final by itself. So let's take this and subtract that from both sides. So I'm going to have 1/2 v initial squared minus g times h final. That's going to equal 1/2 times v final squared. All right, at that point, let's get rid of that 2 by doubling everything. So that 1/2 is going to cancel. That's going to cancel. But that's going to be a 2gh final. So I have v initial squared minus 2gh final equals v final squared. Now, once I've got that, I can square root both sides. And now it's just a matter of plugging in my numbers. I said that he started off with a speed of 5. Notice when I plug in for g, I don't put in negative 9.8. It's a positive number. The minus sign is already there. And of course, h final we said was negative 1.974. And that's fortunate for us because this minus sign and that minus sign, when I multiply them, they'll both turn positive, which is good because I'd hate to have a negative under the radical. That would give me an imaginary velocity. If I was solving a problem and that occurred, by the way, what that would suggest was that he wasn't traveling fast enough to swing up that high. So if you see that, that's something to look out for. So 25 plus 2 times 9.8 times 1.974 is 63 and change. And when I square root that bad boy, turns out that at the bottom of that swing, Spider-Man is traveling about 7.98 meters per second. So the process was super easy. All we had to do was we started with this statement right here, and then we customized it to fill in whatever information we had. And I had to get a little bit clever to figure out the things about the height, but the key point was that I was able to pick a height to call 0 and then measure his other height in reference to that by doing clever bits of geometry. Jasmine, you had a question.
Yeah, so under the square root box, you changed the height back to positive. Is that what you did?
Well, I did, because when I got to this point here, I haven't plugged any numbers in. You see how I have V initial squared minus 2GHF H final?
Okay.
But when I put in H final, the value for H final was a negative number.
Okay, so it just changes.
Yeah, so I ended up having a negative times another negative, and that's why they turned positive.
Okay.
Yeah. If I had made a mistake and not put in H final as a negative number, look what would have happened, right? 2 times 9.8 is about 19.6 times, this is really close to 2, so 19.6 times 2 is going to be just under 40, right? So I would have had 25 minus 40. I would have had a negative under the radical, and that would have been an imaginary number. So had I dropped that minus sign, I would have gotten an error when I plugged it into my calculator.
Okay, got it.
Yeah. And the idea is simple. This minus sign is going to cancel because it makes sense that if Spider-Man starts up here and he starts to swing, there's no reason why he can't swing all the way to the bottom, right? You know he's going to be able to do that. However, he might swing past the bottom and go back up again, and there may be some height that he can't swing past. And how would you know where that height would happen? Well, at that height, what would happen is this number here would turn positive, and it would be bigger than this number here, and we'd have a negative under a radical. That would give me the place where he could swing up to the maximum height when that sign change occurs. So, super easy. We can do these in our sleep. What if I extend this problem out? What if we let Spider-Man start on that building, and instead of swinging down to the bottom, let's have him swing all the way down past the bottom. He's going to swing back up again, and the question is, how high can the building be that he can get up to? So there's going to be some building on the other side, and he's going to run out of steam at some point. And so the question is, how high can this building be? Well, how can we solve this problem here? Well, unfortunately, we don't know any of these angles anymore. That's kind of out of the question. However, we know that he started off over here with a velocity of 5, right? That was given in the original problem. And we could still use energy conservation because his energy before and after are going to have to be the same. Well, he's going to start off with a certain amount of starting kinetic energy, 1/2 mv final squared plus mgh, and not final, initial. He's going to end up, when he swings all the way over here, if he's going to swing as high as he possibly gets, and he can't swing any higher, what velocity would he have at the highest point? Let's hope someone would chime in there. If you're swinging all the way up to the highest point, you're going to have a velocity of 0 at the very end, right? My wife is over here in the kitchen. She's very happy that she knows the answer to that. I know the answer. Yay. You live with a physicist, you pick some stuff up. So that's the idea. He's going to swing all the way up to the highest point. But if that's the case, his final kinetic energy is going to have to be 0. So it'll be 1/2 mv final squared, but I'm just going to make that be 0 because he's going to go as high as he can go. Now, he will have some potential energy, mgh final. And again, I don't know how tall this building is, and I definitely don't know how tall this building is, but here's what I do know. If I call this right here height 0, then h final is going to be however much taller the second building is compared to the original building. So if I know he starts at the top of a 100-meter tall skyscraper, I'll be able to figure out how much taller or shorter the new skyscraper can be. So all I got to do is solve this problem. And again, you'll notice Spider-Man's mass still doesn't matter. And all I got to do to solve for H final is literally divide everything by G. Well, if I divide this by G, I'm going to have V initial squared over, I'm going to put the 2 in the denominator, 2G. Over here, when I take G divided by this, that's just H initial. And of course, we said H initial was 0, right? Oh. So the new final height is going to be whatever speed he has squared divided by 2G. Pretty cool. So that's 25 divided by 19.6. So it looks like he'll be able to swing about 1.27 meters higher than he started at his maximum height. Pretty cool. What if he didn't have a running start? What if he started at rest? How would this answer have changed? Well, if he started at rest, I would have had the exact same stupid equation, except V initial would have been 0. But if this was 0 and this was 0, then H final would have been 0. Well, what does that mean? Well, that means that if he didn't have a running start, if he didn't start with any kinetic energy, he would swing back up to the same height that he had originally. And that sort of makes sense because you started with a certain amount of potential energy. As you swing to the bottom of the swing, your potential energy is getting lower because your height's getting lower, but you're picking up speed. And however much your potential energy goes down by, your kinetic energy will go up by the same amount. Then as you start to swing up from the bottom, your potential energy is starting to get bigger again, but to compensate, the kinetic energy is going down again. And so the potential energy and the kinetic energy are both going up and down in kind of a trade-off. And you'll reach the other turning point when you just run out of kinetic energy and have the same potential energy you started with. You'll be back at the same original height. So I went to grad school in Clemson, and back when I did my very first lecture at Clemson, I was doing it in a lecture hall where we had a pretty cool setup where there was a bowling ball that we could strap that had like a little eye hook on it, and there was a rope that you could hang from the ceiling and hang the bowling ball from the bottom of that rope. And to demonstrate this effect, what you would do is you'd take that bowling ball and you'd pull it back, kind of like Spider-Man is pulled back here, and you'd put the bowling ball at your chin. And the idea is that if I release it at my chin level from rest, it's going to swing away, but it can't ever go higher than whatever height it originally was at. So as it swings away from my face and then eventually swings back, I know intellectually that bowling ball is never going to hit me in the face. It can't go higher than my chin. And so the trick was to look all cool in front of the students. You'd release the ball, you'd let it fly away from you and come back, and you know it's not going to hit you. So you just keep talking the entire time, very confident that you're not going to get hit in the face. Now, it turns out that intellectually, though I knew that I would not get hit in the face, it is extremely hard to have this bowling ball swinging towards your face and not flinch reflexively. So I actually had to practice doing this so that I wouldn't look like a fool and flinch back away and could show my confidence in the physics of this. And it works out pretty great. It's a fun little lecture demo that I wish I could still do at JCSU. There's a video online of another physics professor doing a very similar scenario with one of his students. However, his student makes the mistake of holding the ball and pushing it away from her chin. Why is that bad? Because she's starting with the ball right here. It's got some potential energy and some kinetic energy. It swings away from her chin. It swings all the way away, but now it can swing up to a higher height, just like Spider-Man did in our original problem. Then when it swings back, when it gets to this location here, it's going to have the same potential energy and the same kinetic energy that it had originally, which means it's at this height and it's still moving. So it's pretty awesome. You watch her push it away and the little ball comes back and it hits her in the face and she looks like a fool. I hope she wasn't hurt. I would feel bad laughing at her, if she was actually injured. But pretty cool. So yay, we can do energy conservation problems with impunity. This is all fine and dandy if I have things swinging on ropes, but let's make things more interesting. Because it turns out that when it comes to conservative forces, gravity is not the only game in town. There are other conservative forces that we can talk about, and every conservative force will have its own potential energy expression. Now, we're going to learn 2 of them this semester. We learned gravity. We're going to learn 1 more. Next semester, we're going to come back for Physics 2, and we're going to end up learning about a new force called the Coulomb force. It's the force that positive or negative charges exert on each other. And it turns out that that force is going to also be a conservative force, which means we'll learn a 3rd potential energy formula next semester. So all the stuff we're doing now, we're still going to have to do it in the future, so don't forget it. But we need to come up with an expression for a different kind of potential energy. And that's going to be the potential energy for something that's stretchy, like a spring. So this is going to be the elastic potential energy. Now, in order for us to figure out the elastic potential energy, we need to know, how does a spring or a stretchy object apply forces? How do I know how much force I get from a stretched out spring? And it turns out that springs are governed by something called Hooke's law. Right, it's named after a guy named Robert Hooke. He was a contemporary of Isaac Newton. You guys are mostly biology majors, so you would know Robert Hooke as the guy who invented the term cell, right? We call them cells because this guy gave them that name, right? So, he was a physicist, a biologist. He did science across many different fields. Thank you, sweetheart. And apparently he and Isaac Newton absolutely hated each other. Apparently at different times they were presidents of the Royal Academy of Sciences, and it was traditional in their, I guess, meeting hall or building or whatever, to have portraits painted of all of the previously serving presidents of the Royal Academy of Sciences. And Hooke and Newton just were absolute enemies. They despised one another, and allegedly there was a fire while Isaac Newton was president of the Royal Academy. And as the building is burning down, they're trying to retrieve all of the portraits of various presidents. And Newton would not allow them to go back in and get Robert Hooke's portrait out. They let that one burn because he sucked. So yeah, these guys were petty and terrible. Fun story. But Hooke's law deals with the force exerted by a spring. And what Robert Hooke said was that if you have a spring, well, your spring always has some natural length, right? My spring is some distance long. However, if you take that spring and you either stretch it or compress it and either get it beyond or inside its natural length, so I stretch it out a little bit extra distance. So we'll call that extra distance we stretch it x, that the force that the string exerts is directly proportional to x. In other words, you don't stretch it at all, it doesn't pull on you. If you stretch it some, it pulls on you. You stretch it further, it pulls on you more. And the amount of force you get was given by some constant k times x, where k is called the spring constant. And it's just a number that is associated with that particular spring, right? If k is a big number, that tells you that your spring is a really stiff spring, right? You got to really pull to stretch it out, or really squeeze to squish it in. If k is a wimpy number, then you can stretch it out very, very easily. It doesn't pull on you very hard at all. So the springs in, say, your shock absorbers in your car probably have very large K values. A slinky is a spring, kind of. A slinky would have a very tiny K value. And it just depends on the nature of the spring. It's just a number. So it's K times however far you stretch it. The further you stretch it, the bigger the force. Double this stretch, double the force. Now, there's one last little bit of nomenclature here. And that's that Hooke's law is typically written with a minus sign. Now, what do minus signs represent in physics? It's always about direction. And so to understand why that minus sign is there, think about what's going to happen with a spring. If I have a spring that's naturally this long and I stretch it out X centimeters to the right, so I'm stretching it out this direction, what direction is the spring going to pull me? The opposite way. If I take a spring that's normally this long and I squish it in, well, now I've stretched it, or I've squished it in to the left. What direction is the spring going to push me? To the right. So all the minus sign is saying is that this force that the spring exerts is what we call a restoring force. It wants to go back to its regular length. If you stretch it longer, it wants to make itself shorter. If you squish it in, make it shorter, it wants to make itself longer. It's always going to push in the opposite direction that the spring has been compressed or stretched. And so that minus sign is all about direction. That's all it is. Now, this tells me how much force the spring exerts. What it doesn't tell me is how much work that spring is doing as I compress it. And here's where things are going to get a little bit complicated. Because what's going to happen is if I have a spring and I start it out at its regular equilibrium length, right? So right now, it's not exerting any force at all. And so when I stretch it some tiny little distance to the right, what's going to happen is the force that it's exerting is negative kx, except at first x is 0, right? And by the time I'm done, x is a tiny little bit more than that. The force never gets very big. If I want to know how much work that does, well, the force or the work would be the force times the distance times the cosine of theta. And what's going to happen is my force is super, super tiny because I haven't stretched it very far. So that's super tiny. My distance is super tiny. It's going to do a tiny amount of work at first. Now, what about the cosine of theta? That's the angle between the force and the distance. Well, since my force is, I'm stretching it to the right, so my distance is to the right, the force is back to the left. So the angle here is going to be the 180 degrees between those two things. This is going to equal -1. So the work that I'm going to get done is going to be negative. When I stretch it out, it's going to do negative work. But the amount is not going to be very much because the force was never very big. But now I'm going to stretch it out a little bit further. Now, when I stretch it out another tiny little distance beyond that, well, now, since x is already a little bit bigger, the force is going to be a little bit bigger. And so the work being done for the next little 1 centimeter that I pull it out is going to be a little bit more than it was during the first centimeter that I pull it out. The third centimeter I pull it out is going to be even larger because F keeps getting bigger and bigger and bigger, even though the distance I'm moving is the same. So I'm doing more and more and more and more work. And so most of the work is going to happen out there at the very, very end. And in order for me to actually calculate a number for this, I have a problem. Because F keeps changing, I can't just plug in one number for F. In order for me to do this, I have to do calculus. Calculus was literally invented to solve problems where your formulas had numbers that kept changing as you were doing stuff. So we can't do calculus. This is not a calculus-based class. However, I can be clever about some things. Let's go back and think about how to do this work calculation for another problem that was way simpler than this. Right. So what if I'm doing the work done by gravity of an object that I lift up to some final height. We've done that problem before. We know that the force of gravity is mg. And unlike this force that keeps getting bigger the more I stretch it, the force of gravity is the same the whole way up. It never changed. Which means I can find the work due to that super easy, right? That's just the force, mg, times the distance, h, times the cosine of the angle between those two things. But again, the distance is up, the force is down, so that angle is 180. So the work being done by gravity was negative mgh. And of course, what did we do with that? We said that the potential energy formula was just the opposite of the work, which is why for gravity, the potential energy was mgh. That's where that formula came from. Now, if I were to do a graph of the force of gravity as I'm moving this thing up here, as a function of how high I've lifted it. So if you were the force of gravity as a function of height, at height 0, the force of gravity is mg. At height 1/2 of h, it's still mg. At 3/4 of h, it's still mg. In other words, the force of gravity is a constant. And if I'm going up to some final height, the thing that I notice is that if I look at this little rectangle that's formed on that graph, the area of that rectangle just happens to be this side, mg, times this side, h. Oh, look, mgh. The area of that rectangle is the potential energy. What a coincidence. Now, here's why this is cool. Turns out that's not a coincidence at all. That's going to always be true, no matter how complicated your force really is. So if I'm trying to figure out a potential energy formula for this spring, I want to do a graph for the force exerted by the spring as a function of distance, the same way I did it here. So what would that graph look like? Well, if I don't stretch it at all, if x is 0, then the force will also be 0. So 0, 0 is going to be 1 point. Now, if I move 1 meter and stretch it out 1 meter, the force is going to be 1 times k. So if I go over 1, I'm going to go up by however much k is. If I go twice as far over, I'll go twice as high. What that means is that I'm going to get a straight line. So if Hooke's law is obeyed, my force will be a linear function of the distance, and the slope of that line will equal whatever value the spring constant has. If the spring constant was smaller, then I would have had a shallower slope. Now, here's why that matters. I'm going to do the same trick. I'm going to stretch it out to some x final. And the area underneath the curve is apparently going to equal my potential energy formula. So all I got to do is find the area underneath that. Now, how do I find the area underneath that curve? What's the area of a triangle? Well, we learned it in grade school. The area of a triangle is 1/2 times the base times the height. Now, for this particular triangle, how big is the base of the triangle? Well, the base of the triangle is this side, and this corresponds to however far I stretched it. So this is going to be whatever my final value of x is. Now, what about the height? Well, the height of this triangle is whatever my force is at the very, very end. And my force at the very, very end is going to be whatever my x is times whatever k is. So the height of this triangle is going to be whatever k times whatever x final is. So now I can replace that with k times x final. And when you work that out, you're going to get 1/2 times k times x, so x squared. So this apparently is my potential energy formula for the what we call elastic potential energy. And so anytime I have a spring, I can utilize this to find the energy stored up by that spring. It represents how much work I had to do to squish that spring in or to stretch that spring out. And if I let the spring pop back to its original length, I'm going to get all that energy back. All right. If you had a little brother and you ever shot your little brother with a rubber band, you were utilizing elastic potential energy, because what's happening is when you stretch that rubber band out, you're storing up energy inside that rubber band. The X for the rubber band just got big, and therefore there's energy stored up inside that rubber band, potential energy. When you let go of the rubber band, it snaps back to its original length. So all the potential energy you had stashed up in that rubber band has to go someplace. Where does it go? It turns into kinetic energy, which is why the rubber band goes flying off your finger and hits your annoying little brother. That's the idea. So let's solve a problem with this. So let's do this. Let's say I've got this nice slippery surface, and I've got a box. The mass of this box is, let's say, 3 kilograms. And I'm going to start with this thing 5 meters above the bottom of the ground. And I'm going to let this thing go, and it's going to slide frictionlessly all the way down here, picking up speed the entire way. But here at the bottom, I'm going to have it hit a spring. And it's a pretty stiff spring. Let's let K equal 10,000 newtons per meter. And so what's going to happen is this box is going to slide down here. It's going to hit this spring, and it's going to compress it and squish it in. So the spring is going to get compressed some distance x at its highest value. And at that moment, the box is going to momentarily stop. And I'd like to know how far that spring is going to get squished. So when the box gets here, the velocity of the box will momentarily be 0. And I'd like to figure out how far the spring is going to have to squish before it can cause that box to stop. How will we solve this problem? Well, we know that in this problem, we only have 2 forces that are both conservative. We have the spring, which is conservative. We've got gravity, which is conservative. We also have the normal force, but the normal force usually doesn't do any work, and therefore it's conservative by default. And there's no friction to speak of, so don't have to worry about that. So that allows me to make the statement that for this problem, K initial plus U initial has to be the same as K final plus U final. There's my starting point for every energy conservation problem. Now, I'm starting this box off at rest. And since K is 1/2 mv squared, it's starting off with a V of 0. Its starting kinetic energy has to be 0. Now, what about potential energy? Well, if I'm calling the ground down here height 0, then U initial is going to be mgh initial. So the gravitational potential energy is this. I also should think about the spring potential energy, which is 1/2 kx squared, except that when the box is here, nobody's even squished the spring yet. So originally, the x is going to be 0. So the elastic potential energy portion of the potential energy is going to be 0. But in principle, U initial would have to consist of both this and this. It's just that this one happens to be 0 right now. Now, what about at the end? This guy's going to slide all the way down here, hit the thing, and slow down to a stop, which means its final velocity is 0. That means that the final kinetic energy is 0. What about U final? Well, again, there's 2 parts, gravitational and elastic. But when the box has hit the spring, it's at a height of 0. So the mgh part, that's going to be 0. Meanwhile, the spring has been squished some distance. So that part is definitely not 0. But now that I've expressed that, all I've got to do now is just solve the problem. What am I looking for? I want to know how far the spring got stretched. So I'm looking for x. So all I've got to do is get x by itself. I'm going to multiply both sides by 2. So I'll have 2mgh initial. I'm going to divide both sides by k. Then I'm going to square root both sides. To get x by itself. Now all I have to do is plug in my numbers. H initial was the 5 meters. K was 10,000. And notice the mass of the block did not cancel this time. The mass actually made a difference. So all I've got to do is crunch those numbers. So 2 times 3 is 6, times 9.8, times 5 is 294 up top, divided by a whopping 10,000. Then I got to square root that. And I get 0.171. So how far is that? It doesn't seem like it's very long. Remember, that's 0.71 meters. So that's like 17 centimeters, which is about a little bit more than half a foot. So it's going to go about 6 or 7 inches before it comes to a stop. Now, will the box stay stopped?
Can you say that again?
So the box is going to slide all the way down here. It's going to pick up speed as it goes. It's going to hit this thing and compress it until it goes this distance. And at that point, it's going to have a velocity of 0. But will it stay stopped?
No.
Why not?
Would the spring push it back?
Right, because remember, the spring is now being compressed this far, right? But that means that the spring is exerting a force on my guy this big, k times x. Well, wait a second. 0.171 times 10,000, I don't know why I'm putting this in my calculator because I'm an idiot, is 1,710 newtons. So what's going to happen is, at the moment that this thing momentarily stops, there are forces acting on that box, right? Right, there's a normal force from the ground pointing up, there's gravity pointing down, and these forces might cancel each other out, but then there's this force of the spring pushing really hard to the left. So in the x direction, if F equals ma, F divided by m is going to equal a, so 1710 divided by 3 kilograms, holy crap, that acceleration is going to be huge. So even though it momentarily comes to rest, it only happens for a split second, and immediately it's going to accelerate back out to the left. So what's going to happen is my box is going to slide down here, hit the spring, boing, pop back out, go shooting back out this way, and slide back up. How high is it going to go?
I would assume not that high.
Why not that high?
Because I'm just imagining like actually doing it, and I know like if it get pushed back, it didn't really fall with the same, like it didn't fall with, it fell with a certain force, but coming back, like it would need to have a certain, like, I guess, acceleration to go back up, if that makes sense.
So here's the thing. You're not wrong. In the real world, it will never go quite as high as the 5 meters. However, the reason it doesn't go quite that high is because in the real world, there's friction. And friction is a non-conservative force. And this equation that says the energy before equals the energy after is only true if the friction is negligible. So in reality, it'll go a little bit smaller than 5 meters. But if we lived in a perfect frictionless world, the best we could ever hope for is it would go back up to the very original height. Because remember, it started off with a potential energy of mgh, and that was the only energy it had, right? When it hits over here, bounces and comes back, it's going to have the same energy, which means we expect it to go back up to that same height. So ideally, the highest it would ever go up is 5 meters. And that's if everything was perfect and there were no non-conservative forces. But, and I'm glad you mentioned this because it's where we're going next, what happens if there really are some non-conservative forces? What if I can't ignore all the friction that happens along the way? Well, obviously, it won't slide quite as high up the other side, but instead we'll lose a little bit of height. And we need to figure out, like, how can I correct for that? Can I still use energy conservation to solve a problem, even if I know that there's non-conservative forces?
Okay. Before we move to the next thing, could you show the force, the free
The
body
Hooke's law?
diagram?
Oh, the free body diagram. Yeah. So yeah, at the moment when it comes to a stop, at that one moment in time, the force was this big, right? It was 10,000 times x. And it was to the left, and there's no other forces to the right to cancel it out. So in the x direction, the net force is just the 1710. So it's going to have a huge acceleration. It's going to stop, but almost immediately go zooming back to the left.
Okay, thank you.
You're welcome. All right, so what happens if I've got non-conservative forces? Turns out energy conservation will still be useful, but only if we're clever about it. Because if there were nothing but conservative forces, we were saying that the starting kinetic energy plus the starting potential energy is going to equal the ending kinetic energy plus the ending potential energy, right? If there's no non-conservative forces, this statement will be true. And the energy I start with will equal the energy I finish with. However, if I have some non-conservative forces, what's going to happen is they can sometimes either take away energy so that the ending energy would be less than the starting energy, or they might give me energy that I did not have originally. Now, to give me a sense of how that's going to play out, think about friction for a second. We know that friction is a non-conservative force, right? It does not obey this rule that the work done over any round trip is always zero, because if I drag my pen to the right a certain distance, and let's say the friction did -5 joules of work, when I slide it back, it's going to do negative work on the way back as well, because the friction is always opposing the motion. So the angle between F and D was 180, both on the way out and on the way back. And -5 plus -5 is -10. That's not zero. Gravity, when I lift something up, does negative work. When I drop it back down, it does the same amount of positive work, so that the total was always zero. So turns out that my starting energy and my ending energy, they can be different. But the cool part is that they can be different by however much work that non-conservative force did. So if I have a non-conservative force, and that non-conservative force is like friction and it's doing negative work, then that means that I may have started with, let's say, 1,000 joules worth of energy. But if the friction did, say, -100 joules of work, then I would end with 100 fewer joules. In other words, this final energy would have to be smaller than my starting energy by 100. I could make this equation work then if I just added the work done by the non-conservative forces over here. Notice, if this WNC is a negative number, then I would take my starting energy plus a negative number would equal a smaller ending number. So it'll get me the right answer if the work being done is negative. But it will also work if the work being done were positive, right? If I started with 1,000 joules, and then the non-conservative forces were also providing me with an extra 100 joules, then my ending energy would be 1,000 plus 100. So either way, whether the work is positive or negative, this expression will still work. So this I can use even if I have a non-conservative force like friction. in the mix. Now, let's solve this problem. Let's do this. Let's imagine that I've got the same kind of bowl, but let's take the spring out of it, and let's just have the bowl swing up the other side. If I start this thing with a height of 5 meters, if there were no friction, that means there's no non-conservative forces, WNC would equal 0, and I'd have the same starting point that we have for all these energy conservation problems. And if I wanted to figure out like how high up the other side this object's going to slide, well, at its highest point, it would have a velocity of 0. I'd be solving for H final. And so if there were no non-conservative forces, I'd solve this. K initial, I'm starting from rest, would be 0. So I'd have 0 plus mgh. K final would equal, well, I'm starting at a velocity of 0 here, so that would be 0. Plus this would be mgh final. And this is like the easiest problem to solve ever because the m's and the g's cancel. So if there were no friction, I'd expect H final to be the same as H initial, which again makes sense. If there was no friction on this little bowl, this guy would just go sliding down. He'd pick up speed, then he'd slow down, then he'd pick up speed, then he'd slow down. And it would just swing back and forth, back and forth, back and forth, back and forth forever. It would always go up to the same starting height every time before it turns around. However, if I've got friction, that changes things a little bit. So let's do this. Friction is annoying because as a non-conservative force, the amount of work done depends on the path. So we would care about like the curvature of this thing here if there was friction on the curvy part. So to make things easy, let's assume that this little part right here where it's flat, that's where we have friction. So there's friction on the flat spot and the curvy parts are still slippery. That'll make the math easier for us to do. Let's imagine this guy right here is a distance of, I don't know, 30 centimeters. So I got a 30 centimeter wide patch where there's friction, and over that patch, the coefficient of kinetic friction is, let's go with 0.4. So far, so good. So in order for me to solve this problem, I'm still starting with this, but now I've got to deal with this term there. It's going to be similar to what we did for the non-friction side, but now let's box that off so we don't look at it anymore. K initial still 0. K final still 0. That's simple. This is going to still equal mgh initial. That's going to still equal mgh final. But I got to fill in this blank over here. And in order for me to find the work done by friction, I know that the work is the force times the distance times the cosine of the angle between the force and the distance. So I'm going to save the force for last because it's the most complicated part. What about theta? What would theta be? Well, as it's sliding across here, the distance that it's traveling is to the right, but the friction is going to pull it to the left. So the angle between this and this is 180 degrees. The cosine of 180 is -1. So this turns into a -1. D is easy. It's the distance over which the friction acts, which in this case is 3 centimeters, or in SI units, 0.03 meters. So D, that was super easy. Now, for the force of friction, we remember from chapter 5 that the force of friction is the coefficient of friction, aha, that's given, times the normal force. We don't know what the normal force is. So in order to figure out the normal force, let's think about this in terms of Newton's laws for a second. Here's my box sitting on the floor. What are the forces acting on it? I got a normal force pointing straight up. I got gravity pointing straight down. I got friction to the left. And if I do F equals ma, in the y direction, I only have two forces. The normal force up minus gravity down. And in the up and down direction, the acceleration has to be 0 because it's not going to fly off the floor or sink into the floor. So N minus mg equals 0, which implies the normal force has to push up just as hard as gravity pulls down. So heck, now we know the normal force. So the force of friction is going to be mu k times mg. So now, if I'm doing WNC, the work done by the non-conservative forces, it's going to be the force of friction, this, times the distance, d. However, it's times the cosine of 180, which is -1, so it's got a minus sign. And now, look what just happened. Notice all 3 of these terms have m's and g's in them. So all the mg's are going to cancel. And I get that my final height is going to be my starting height minus mu k times d. So this is how much less height I'm going to get because this is related to how much energy the friction takes away. So if I started off at a height of 5 meters and 0.4 times 0.03, it's going to go up to a height of 4.988 meters, which, as we expected, is a little bit less than what we started at. The more friction there is, if I made this friction value higher, it would have shrunk that down by a little bit more. If this had been wider, if I had more distance over which the friction was acting, that would have shrunk down from 5 a little bit more. So all we had to do was do the energy conservation problem and then just figure out the work done by the non-conservative forces. And that required me to go aside a little bit and do the FD cosine theta deal. But other than that, super easy. So far, how are we doing?
I kind of get it.
It's not hard. It's not hard. So that's what you'll end up doing for energy conservation problems. There's one more big concept that I should probably address. We don't do a whole lot with it this semester, but it will become important next semester, so I should probably spend some time on it. And that's the concept of power. Now, in physics, power is a rate of change. Right? Power is a rate. Now, what do I mean when I say something is a rate? Well, rates always happen as something per something, right? If you travel to Europe and you're turning your dollars into euros, there will be an exchange rate. You'll get a certain number of euros per dollar that you turn in. If you work a job, you might get paid an hourly rate of X number of dollars per hour that you work. So the same thing is going to be true here. Power is going to be the rate at which energy is provided or expended. So power will be defined as the amount of energy or work per time. That's the idea. Work over time. Now, work, of course, is measured in joules. That's the SI unit. Time is, of course, measured in seconds. So power will be measured in joules per second, and we're going to give that a name. That is called a watt. So you can see why this is going to be important for next semester, because when we're dealing with electricity and magnetism, we'll often measure things in watts. Think about when you go and you buy light bulbs, right? Light bulbs are often rated by how many watts of power they deliver. This is a 100-watt bulb. That means that it's providing you 100 joules of light and heat per second that it's on, whereas a 60-watt bulb only provides 60 joules every second. So there's less energy, therefore less light coming out at a lower wattage. But that's the basic idea. Now, I taught a few semesters at CPCC, and one of the labs that they have them do that I've thought about inflicting on you guys, and I've never actually done it, was we had students figure out how much power they were capable of generating. Now, how would I do that? How could I figure out how much power you guys could put out? Well, one way was to give you a task where you had to do a certain amount of work. And the task that we used to do in this particular lab was we had these guys run up some stairs. So if you were to walk up a flight of stairs, how much work would you have to do? Well, here's a flight of stairs. And in order for you to get up those stairs, you're going to have to provide some kind of force. And even if you go up the stairs at a constant speed, what's going to happen is gravity is pulling you down. And so you'd have to provide a force upward that is at least as big as gravity. So the bottom line is you have to go upward with a force equal to mg. And of course, you're going to rise to a height h. Oh, duh. If I want to walk up a flight of stairs, the amount of work that I'm going to have to do is going to equal how much potential energy I'm going to have at the top. Duh. So the work that I'd have to do to go up those stairs is mgh. And so we would do that. We'd go to the stairs, we'd measure the height of the stairs, and we'd have them go up a flight of stairs. And notice, if you got a bigger mass, it's going to take you more work to go up those stairs. A fat guy like me has to do way more work to go up the stairs than a little skinny person because I got a bigger M. Now, here's a question. If I run up the stairs at a constant speed of 5 meters per second, will that require more or less work than if I walk up the stairs at 2 meters per second? Which is going to require me to do more work? Running up the stairs at 10 or walking up the stairs at 2 meters per second?
I'm sorry, can you repeat that one more time?
Mm-hmm. So I want to know, in which of these cases would I have to do more work? If I run up the stairs at 10 meters per second, or if I walk up the stairs at a constant speed of 2 meters per second? Which of those is going to require that I do more work?
Walking up the stairs?
I'm going to do more work walking than I do running? Convince me.
I'm just thinking about, because you said constant, so I guess like in my mind I'm trying to think like you will be going kind of slower, which means you will be going kind of longer up the stairs, I guess.
So you're answering a different question though, because notice the amount of work that it takes me doesn't care about how much time it takes. Time is where it's going to come in when I come to power, and I haven't asked you about power yet.
Okay. Well, then running up the stairs.
Well, hang on a second. The amount of work that it takes to go up those stairs is going to be m times g times h, right? Where's the velocity show up in the formula? It doesn't, right?
Mm-hmm.
Which means the amount of work it takes to go up those stairs is going to be the same whether I walk them or whether I run them. It's not going to matter, because in each case, I'm traveling up the stairs, doing a certain amount of work to get up to that height. The more stairs I climb, the more work I'm going to do. But how fast I do that work doesn't matter. So in terms of the amount of work, it's going to be the same whether I'm walking or whether I'm running. Now, if I run up the stairs, what's going to happen is maybe it takes me 10,000 joules of work to go up those stairs. In fact, for me, let's imagine the stairs are 3 meters tall. It would take me more like 3,000 joules. 3,000 joules to run up those stairs. And it's going to be the same whether I walk or whether I run. Now, the difference is if I walk up the stairs, I'm going to do that 3,000 joules worth of work in a very long amount of time because I'm going slow, right? That means the power that I have to that I require is going to be lower. If I run up the stairs, I'm going to do the same amount of work in less time. That's requiring more power. So power is going to be related to how long it takes to go up the stairs. I can do the same amount of energy over a longer time, and it requires less power. Does that make sense?
Yes.
Yeah. There's an experiment that I know I've seen Dr. Kern do it in one of their classes, where they take, I think it's potassium nitrate and gummy bears, right? Now, when you eat a gummy bear, what happens? Right? You're metabolizing the sugar in that gummy bear, and there's a certain amount of energy stored up in the bonds of those sugar molecules. And so what's happening is inside your body, you're breaking those sugar molecules down. You're releasing a certain amount of energy. It takes work to do that, right? You're breaking that down, and you get a certain amount of work out of that gummy bear as you metabolize it. Now, the amount of that work is some number of joules, and your body is metabolizing that over a long period of time. So it's providing a certain number of joules over an extended period of time. The power is low. What they were doing in the experiment was they'd take those same gummy bears and they'd use potassium nitrate to react with it. Now, the energy you can get out of that gummy bear hasn't changed. You're getting the same energy out of it in that reaction that you would if you just ate the gummy bear. The difference, though, is that this potassium nitrate reaction happens super, super quickly. And as a consequence, what would happen is gouts of flame would be exerted and expelled out of this little test tube with the gummy bear in it. It literally explodes. Same energy in that explosion as you got when you ate the gummy bear. The difference is that this explosion happens over a tiny period of time. The metabolism happens over a much longer period of time. Same energy, more power. Does that make sense?
Yes.
And it turns out that when you guys talk about like calories in terms of eating things, well, those calories are a unit of energy. Just to give you a sense of things, the reason that we name the unit of energy the joule is after a guy by the name of James Prescott Joule. And for my money, James Prescott Joule is one of the coolest physicists in the history of physics. And the reason he's so cool is because back in his time, which was the mid 1800s, probably actually mid to late 1800s, I guess, we're just gearing up towards the Industrial Revolution. We're learning how to use machines to mechanize certain processes that we had been doing for centuries prior to that in less efficient ways. And most physicists at the time didn't do physics as their day job. It was a thing that they did as a side project, and their day job was something else. And in the case of James Prescott Joule, his day job was he brewed beer. He was working for a company, and they were trying to figure out how to make beer at an industrial scale. Because, I mean, beer is like 5,000 years old. People like millennia ago could make beer, but you usually did it in small batches. And they wanted to be able to do beer in gigantic vats that you could just put in a factory and churn out gallon after gallon after gallon of beer constantly. But in order for that to happen, you've got to have this fermentation process happen. And you need to have your big vat full of fermenting stuff at a reasonably uniform temperature so that your yeasts are happy and they're constantly breaking down sugars and creating alcohol. And if you don't have the temperature control well, it doesn't go very well. And in these large vats, what's going to happen is you had to worry about stuff settling at the bottom and all the reaction happening at the bottom of the vat, and the top of the vat is maybe a different temperature than the bottom. And because of that, they would put these big mechanical stirrers inside the vats of beer to stir it up so that the warmer stuff at the bottom would get pushed up to the top, and so you'd have a more uniform temperature throughout the entire vat. over a smaller batch, it wasn't that big a deal because the whole batch wasn't very, very big. So the temperature gradients could never get very large. But at an industrial scale, it mattered if you didn't stir it. The problem, though, is that Joule is trying to build these mechanical stirrers, and every time he turns on the stirrers, the temperature of his beer starts to go up. And he's like, this sucks. I'm trying to stir this, and my temperature is getting all wonky. So what's going on with that? So what Joule does is he says, okay, let's simplify this. There's too much going on in this process with the beer reaction. So let's pull all the beer out of the vat, and let's just throw in water. Just plain old boring, non-chemically active water. And what he did is he put these big tanks full of water, he turns on the stirrers, and he measures how much the temperature of the water goes up. And what he finds is that there is a relationship between the temperature that the water goes up to and how much work the stirrers are doing. And what he finds is that it takes 4,184 joules of work to raise 1 kilogram of water by 1 degree Celsius. So 1 gram took 1,000 times less. So this amount of work caused 1 gram of water to go up by 1 degree Celsius. That's the thing he found. And what he realized was that heat or temperature is really just another form of energy. It was a form of work. Work could turn into temperature and vice versa. And that was pretty phenomenal at the time, because at the time people didn't really understand what heat was. People thought of heat as being this weird sort of invisible fluid that either leaked into or leaked out of things. And what was baffling about this beer experiment that he was doing was that he's turning the stirrers and the water is getting hotter, but there's nothing else around it that's getting colder. So he couldn't really say, oh, heat's flowing from the cold thing into the hot thing. That wasn't happening. It was like the heat was coming from nowhere. So he realized that this is what we call the mechanical equivalent of heat. And of course, this many joules, we give it a name. We call it 1 lowercase c calorie. Now, what's going to happen is, obviously, if I have 1,000 of these, like I do up here, this would be what we would call in the metric system 1 kilocalorie. However, because nutritionists are annoying, rather than just call it a kilocalorie like a normal person would, they call it a capital C calorie. So a capital C calorie and a kilo lowercase c calorie are the same thing. But each of those are a unit of energy. And so when you look on a package of something, so here's a bag of Doritos that I ate beginning of class. According to this, it's 150 capital C calories, which means eating that bag of Doritos is going to give me, well, that's capital C, that's actually 150,000 lowercase c calories times 4.184. That's a whopping 627,600 joules worth of energy that I'm deriving from that stupid bag of chips. Now, what's happening to that 626,000 joules of energy? Well, I use some of it for getting up and moving around, so I can turn that into kinetic energy. Some of it is going into heat, right? The fact that I have a 98.6 body weight temperature is being fueled in part by me metabolizing junk food like this, right? So that's what we're doing. We're converting that process. So when you see calories, bear in mind that calories are just another unit of energy, not unlike the joule. Now, if we can use work and measure work in unusual units, we can also measure power in unusual units. So I should probably point out that one of those you see a lot is called the horsepower. 1 horsepower is 746 watts. Why do they call it a horsepower? Well, it's pretty obvious. Imagine you're John Deere and you've just invented the tractor in the late 1800s, and you're trying to convince a bunch of farmers who have horses who can pull their plows just fine that they need to buy your big expensive piece of equipment and plow their fields with a tractor rather than just use their horse. The farmers are, of course, going to be reasonably skeptical and say, look, dude, I got a horse. He's easy and I don't have to pay anybody for him. You know, I need to get a new horse. All I got to do is breed him and he'll have babies. I get a new horse. You know, your tractors don't self-replicate. So what do you got to do? You got to prove that your tractor can do the same work as your horse. So you take your horse, you have the horse pull the plow with a known amount of force, plow a field in a certain amount of time that takes a certain amount of work, force times distance. Then you show that your tractor can do the same force times distance in less time because it's got more power. And this apparently is the typical power that a horse could provide in watts. So those, again, just are all unusual units. We don't do a whole lot with power or horsepower, but you should probably be aware of it. One last little trick with power, and we'll call it a day. Oh no, did I run out of pads? There we go. This one. So if power is equal to work over time, but work is force times distance, well, what if I just group this differently? What is that? Distance over time. That's a velocity, right? So we can say that the power is force times velocity. Now, why would I ever use this? What's this good for? Well, imagine that I've got my car and I want to drive my car down the road at some constant speed. Now, what's preventing me from doing that? Well, as I drive my car, it's going to have to deal with things like friction, rolling friction from the tires, trying to slow it down, or perhaps more importantly, things like drag, right? That drag force is constantly slowing me down. And so what's going to happen is, in order for me to travel at this constant speed, I'm going to have some forward force provided by my engine to oppose that drag force. So if I'm going to travel at a constant speed, the force that my car pulls forward minus the drag force has to equal ma. At constant speed, a is 0. So I got to push my car forward with at least as much force as the drag force. And of course, the drag force is equal to 1/2 CA rho times, let's call it V squared. So my car has to provide that amount of force. And what's going to happen is, depending on the engine of my car, it may not be able to provide that much force. And in fact, this tells you why some cars can drive faster than others. Because let's say that I know the horsepower of my car. So if I do that, let's see here. I drive a Prius. So I'm looking up, according to Google, my little Toyota Prius can provide me a power of 121 horsepower. Now, let's compare that to a Corvette. A Corvette can put out a whopping, let's call it 495 horsepower. So obviously, the Corvette ought to be able to travel faster than my car. Well, how much faster? Well, we can figure at least some of that out. So since the power should equal the force that I can exert times my velocity, and the force that I have to exert with my car is going to equal the drag force, then I can say that the power should equal the drag force, 1/2 CA rho V squared, times V, which is going to make that be V cubed. And what that means is that if I solve this for the velocity, that's going to give me the highest velocity I could possibly have, because that's the place where these two things exactly equal. I can't speed up anymore. So 2 times P divided by C A rho cube rooted, that's going to be the top speed of my car. So notice what's going to happen is, even though the Corvette has more than double, heck, it has more than triple my horsepower, it's not going to be able to go triple my speed, because I'm going to have to cube root that. And what's going to happen is the density of air is going to be the same for both cars. The area is going to maybe be different. The coefficient of drag is going to be different, because that's going to be how aerodynamic the cars are. But even if we assume these are the same, the horsepower alone is going to account for a difference. But what's going to happen is, if I do the velocity for my Prius, that's going to be 2 times the Prius horsepower. I'll call that P sub P over CA rho. The velocity for my Corvette is going to be 2 times the power of the Corvette over CA rho. And what's going to happen is, if these two formulas are so similar, one trick that I often will use is I'll divide one by the other. That way, all the stuff they have in common will cancel out. So VP over VC is going to be the cube root of 2 times the power of the Prius over CA rho. But then I multiply by the reciprocal of the bottom. So it's going to be CA rho over 2 power of the Corvette. And notice all the garbage that's in common is going to cancel. And I'm going to end up with just the cube root of the ratio of the powers. So if I want to figure out the top speed of the Prius over the top speed of the Corvette is equal to the cube root of the ratio of their powers. I'm just getting V Prius by itself. And so now what's going to happen is, the power of the Prius was 121. That was 495. So 121 divided by 495 is about 0.244. I've got to cube root that. So that's about, this whole thing right here is about 0.625. And so what this tells me is that my Prius can probably only have a top speed of about 63% of the top speed of a Corvette. That I can totally believe, right? Notice, even though it's got more than triple the horsepower, it's got not quite double the top speed. And that makes sense because of that cube root factor. So why would I use this F times V formula? Oftentimes it's going to be with situations where I have to maintain a velocity in the face of some constant opposing force, not unlike the drag force. All right, so in terms of chapter 7, we pretty much hit it all. That's about all we're going to do with chapter 7 and energy conservation. So if you haven't already, make sure you take a crack at those chapter 7 homework problems. Tomorrow we will start chapter 8, which is going to be another conservation law, but it's going to be a conservation law called momentum conservation. And it's going to give us, just like energy conservation, it's going to give us the ability to solve certain problems that Newton's laws alone would make really, really hard. And it's going to turn those hard problems into really easy problems. All right, any last minute questions?
I have to go to your office hours.
I figured. All right, that's it. I'll see you tomorrow. Have a good day.